Good morning, friends. In last lecture, we had seen a problem on cantilever slab. Now, on the same line, we'll see the second problem on cantilever slab. See, the problem is given as design a cantilever chhaja with the following data. That is, data is given span 1.2 meter. See here, only span is given, not effective span is given. Live load 2 kilonewton per meter square. Floor finish 1 kilonewton per meter square. See, live load and floor finish are given separately. In last problem, the live load and floor finish is given in terms of addition. That is, the total load is given. But here, the live load and floor finish are given separately. Width of support, that the cantilever slab is resting at one end and free at the other end. For that, where the cantilever slab is resting, that support width is 230 mm by 430 mm beam. Draw the reinforcement details. Use 10 mm diameter bars and Fe415 and 6 mm bars of Fe250. That is, main steel we have to use is Fe415 and mild steel for distribution steel. Use M20 grade concrete, that is FCK is given as 20 Newton per mm square and Fy as 415 Newton per mm square. See, this is the cantilever. In last lecture, we have seen the diagram. This is the supporting beam. This is the beam. This is beam. That beam width is 230 by 430 mm. That is, depth is 430 mm and width is 230. This is the main steel always provided at the top for cantilever, while in one-way slab the main steel is provided at the bottom and distribution is up. But for cantilever, the main steel is provided upward side and distribution below the main steel, because the bending is in this direction. So upper layer gets elongated and bottom layer gets compressed. So where elongation is there, tension is there. So tension at side, we have to provide the steel. Again, every third bar is bent up bar. This is the main steel. After every third bar, again there is a bent up bar. This bars in local language, it is also known as chimta bar. Okay. Then distribution steel 6 mm. These are the distribution steel. These spots are distribution steel. Okay. Then we'll start with the problem. In the given problem, shorter span is 1.2 meter, live load 2 kN per meter square, floor finish 1 kN per meter square, materials used are M20 and Fe415, FCK 20 Newton per meter square, Fy 415 Newton per meter square. To find design of cantilever slab for chhaja. It is also known as cantilever slab or chhaja, or slab projection or veranda or windows. It is also known as chhapri. Okay. Then as usual, for one-way slab and cantilever slab, all steps are same except the calculation of bending moment. For one-way slab, the bending moment is calculated by using the formula WL square by 8, while for cantilever slab, we have to calculate the bending moment as WL square upon 2. This is very important. Again, here this depth is a trial depth, that is assumed depth, not the required depth. This is the trial depth. This depth you can assume directly without taking this L by D ratio, and this depth you can consider from 75 mm to 100 mm directly, or you can go through this formula, basic formula, that is trial depth formula, that is D is equal to span upon basic L by D ratio into MF, and this basic L by D ratio for cantilever slab is taken as 7, modification factor, it is depends on the percentage of steel and is given as 1.6. From this calculation, the D assumed, that is effective depth assumed, is 92.2 mm, say 110 mm. Then overall depth is calculated by adding the cover plus half of the diameter bar, main steel bar, and that overall depth is nearly equal to 130 mm and the effective depth is 110 mm. This calculation is wrong. The total effective depth is 107.1 mm and say 110 mm. Adding the effective cover, directly you can get the overall depth. This is the effective depth and this one is the overall depth. Then we have to calculate the effective span, because in first problem we have given directly the effective depth as 1 meter in first problem, but here we have given only span, not effective span. So we have to convert this span into effective span. So L effective is equal to L, that is given length, the given span, plus D assumed, that is effective depth assumed by 2, that is 110 by 2, that L effective is equal to 1255 mm, that is L effective 1.255 meter. This is the L effective. Then loading for 1 meter wide strip, again we are considering 1 meter width of the slab. From that we have to calculate the total load acting on the cantilever slab. The total load is, first load is self weight, that is weight density of concrete is 25 kN per meter cube. Overall depth capital D as 130 mm, that is 0.13 meter. Width we are considering as 1 meter. So total self weight is 3.25 kilonewton per meter. This is the uniformly distributed load since its unit is kilonewton per meter. Live load 2 into 1, 2 kilonewton per meter square, it is given in the problem, into 1 meter is the width of the slab, that is 2 into 1, that is 2 kilonewton per meter. Floor finish is given as 1 kilonewton per meter square into 1 meter width, that is 1 kilonewton per meter. So total load acting on the cantilever is 3.25 plus 2 plus 1, that is 6.25 kilonewton per meter. Therefore factored load, that is ultimate load, is 1.5. This is the factor of safety for load, that is 1.5 into 6.25, it gives 9.375 kilonewton per meter. This is the total load acting on the cantilever slab. For this total load we have to calculate the bending moment, ultimate bending moment acting on the slab. So factor moment acting on the cantilever slab, that is MD, is given by WL square by 2, that is ultimate load 9.375 into 1.255 square divided by 2, that is 7.38 kilonewton meter, that is 7.38 into 10 to 6 Newton mm is the ultimate moment acting on the cantilever slab. So for this ultimate moment we have to calculate the depth required. Actually in first step we have calculated trial depth, that is assumed depth, that depth only assumed depth. For this bending moment we have to calculate the actual depth. So equating mu and mu limiting, since the given steel is Fe4 on 5, for Fe4 on 5 the ultimate moment of resistance or mu limiting, the ultimate moment limiting moment is 0.138 fckb square. So put the values here and calculate the D required. Actually the D required is 51.72 mm, say 55 mm or 60 mm. So in first step we have assumed this D assumed as 100 mm, but required is only 51.72 mm. You can directly use this value while solving the problem, no problem at all. You can use 51.72 as it is while solving the problems, because this is the required depth only and this is the assumed depth. But for factor of safety again we are going to increase the depth so it can bear maximum bending moment or maximum load on it. So this is safe for bending. Then calculation of main steel area. Again same formula as it is used in first problem or for one-way slab. That is AST main 0.5 FCK upon Fy into bracket 1 minus under root of 1 minus 4.6 mu upon FCK BD square bracket complete B into D. Then total calculation is 192.94 mm square. You check this calculation very accurately. Sometimes these values are wrong, but you have to correct it. That is very important. So this is the main steel area. Then check for minimum steel for Fe4 on 5. Since we are using Fe4 on 5, that is torch steel, for this minimum steel area is 0.12% of gross area, that is B into capital D. This is capital D, this is width is 1 meter and overall depth is 130 mm. So main steel is 156 mm square. Since AST is greater than AST minimum, hence okay. Then spacing for main reinforcement of 10 mm diameter. So same formula we are going to use for calculation of spacing of main steel as the distribution steel. That is S is equal to B into area of 1 bar, that is A5 upon total AST of main steel. The 100 into pi by 4 in D square, 100 into pi into D, diameter of bar we are considering as 10, that is 10 square divided by 4, divided by total AST 192.94. So spacing is 407 mm, and this spacing must be taken minimum of 3D or 300 mm. That is 3 into D. D is the effective depth, that is 100, that is 300 mm or 300 mm. So here spacing is 407 mm, but the minimum spacing required is 300 mm. So we have to provide 300 mm as a minimum spacing, not 407. So therefore S is equal to 300 mm. Provide main reinforcement 10 mm diameter at a spacing of 300 mm center to center. Then calculation of distribution steel. Since we are using 6 mm diameter bar, the distribution steel is taken as 0.15% of gross area, that is 0.15%, that is 0.15 divided by 100 into B into capital D, that is 1000 into 125 mm, that is AST distribution 187.5 mm square. See here, the overall depth is 130 mm. Check it and put here 130 mm and then calculate the distribution steel. Okay. Then spacing of distribution steel, same formula. Spacing S is equal to 1000 into area of 1 bar upon total AST of distribution steel, that is 1000 into 28.27, that is pi by 4 into D square, that is pi by 4 into 6 square, that comes to 28.27, and minimum steel for distribution steel is 187.5. So S is equal to spacing 150.70 mm, say 150 mm, and it is the minimum for 5D or 450 mm, whichever is less. Therefore provide main reinforcement, provide distribution, not main reinforcement, it is the main reinforcement for distribution as 6 mm diameter at a spacing of 150 mm center to center. So finally the summary: depth of slab 130 mm, that is overall depth, cover 15 mm, main steel 10 mm at 300 mm center to center, and distribution steel 6 mm about 150 mm center to center. Thank you.